to introduce Yann Bugeaud, who talk about the Littlewood conjecture, so around the Littlewood conjecture.
Okay, thank you. Thank you, Gugu, and thank you, many thanks to the organizers for this very kind invitation. So, as Gugu said, I will speak around the Littlewood conjecture in different time approximations. So first, some notation. With double bar, I denote the distance to the nearest integer. And the Littlewood conjecture is the following problem. So take alpha and beta real numbers. Is it true that the infimum over all integer q of q times q alpha times q beta is 0? Okay. So you know that it follows from the theory of continued fraction that this infimum is at most equal to 1 for every irrational alpha. So the question is, if we multiply by this quantity, which is less than 1, so shall we reach or not 0? So the answer is yes in some easy case. So yes, obviously, when alpha or beta is not badly approximable, so I recall that the set of badly approximable number is a set of real number psi, such that this infimum q psi is strictly positive. So it has Lebesgue measure 0, but has full Hausdorff dimension, so it's quite large set in this sense. So the possible exceptions to this conjecture are when alpha and beta are in bad, so we can restrict our attention to this case. And also it's quite obvious also that the conjecture is true when one alpha and beta are linearly dependent over Q. So the first result was proved by Castles and Swillerton Dyer in 1955. And they proved that the Littlewood conjecture holds when alpha and beta are in the same cubic field. Well, in this case, we don't know whether alpha and beta are badly approximable or not. And then afterwards, there was essentially no further result until 2000, where there was a nice metric result by Pollington and Villani. And the most striking recent result in this direction was proved by Einsiedler, Katak, and Lindenstrauss, (2006), and they prove that the set of exceptions alpha beta, pairs alpha beta, to the Littlewood conjecture as of dimension 0. So the set of possible exceptions is very small. Doesn't mean that it's empty. And also, I like to point out that we don't know whether the conjecture is true when, for instance, alpha is root 2 and beta is root 3. So in the case of when alpha and beta are quadratic and not linearly dependent over Q, then the problem is still open, completely open. Actually, the result was a bit more general, and in the proceedings of the ICM in 2010, Lindenstrauss wrote another theorem related to the Littlewood conjecture. It's nice, I think, a nice way to state the actual state of the art. So for this, I will introduce some notation. So take a use continued fraction to express a real number. I assume that my numbers are between 0 and 1, which is absolutely not important. And consider the complexity of psi. So P of psi is the number, the psi in band, is a number of blocks, different blocks of length n, composed of consecutive partial quotients. So you consider the sequence of, you view the sequence of partial quotients of psi as an infinite word on a finite alphabet, because psi is assumed to be in bad. And you count the number of distant blocks of length n that you see when you move a window along this infinite world. So, for instance, if AG is less than capital M for every G, then it's clear that Pn of psi is always at most equal to M to the n. Okay. Then you can define the entropy of psi which is the limit when n tends to infinity of the logarithm of Pn of psi divided by n. Okay, so this limit exists because this function is subadditive. This one is submultiplicative. Okay, so the result is the following. If the entropy of alpha is positive, or if the entropy of beta is positive, then the pair alpha beta satisfies the Littlewood conjecture. Okay, so it means that if one wants to find a counterexample, we have to consider alpha and beta with low entropy. For instance, like I said, quadratic numbers, or maybe Stromian numbers, well, Stromian continued fraction. So this is essentially the state of the art. And now I will discuss a related conjecture which was introduced in 2004 by de Matin and Tellier. So you take P a prime number, you consider the periodic absolute value. So if, for instance, you have an integer x, can be written as p to the a times p tilde, where p doesn't divide p tilde, then the periodic absolute value of p of x is p to the minus a. Okay. You take a number, a real number, alpha, and the question is the following. Is it true that the infimum over every positive integer q of q times q alpha, so as I said, this is at most 1, and then you multiply not by q beta, but by the qp, which is less or equal to 1 for every q and every p. So is it true that this infimum is always 0? So this question seems to be a bit easier, in the sense that it seems easier to control this qp than this q beta. But actually, essentially, the state of the art regarding the two conjectures is more or less the same. So we face more or less the same difficulties. So, but I will begin by an observation. You may ask, if you consider the Littlewood conjecture, what happens if you multiply then by q gamma, q delta, and so on? So if you consider a finite set of numbers multiplied by more than two numbers. And actually, nothing more is known, so we cannot say anything more. But here, if you take 2 primes, then it's easy in some sense. So there is a theorem. So P1, P2, so distinct primes. And for every alpha, the infimum of a q of q alpha, qp1, qp2 is 0. And the proof actually is easy, and it uses a theorem of Fürstenberg, saying that the set of fractional part P1 to the m times P2 to the n times alpha, where m, n are positive. So this set of fractional part is dense in 0, 1. It's dense in 0, 1. Okay, to go from here to here, you take for Q simply P1 to the m times P2 to the n. And these two terms will compensate the Q. And since this sequence is dense in 0, 1, this term here will approach 0 as close as you want. So the infimum is indeed 0. So this was observed by Einsiedler and Kleinbach. Okay. Now, some results. So the analog of the result of Castles and Swinert and Dyer was proved by De Matin and Tellier, and they proved that this is true if alpha is quadratic. And there was subsequently some other classes of alpha which satisfies the, say, mixed Littlewood conjecture for every prime p. That I worked on this with Bernard de Matin and Michel Motta, for instance. And as for a metrical result, yeah. Quadratic. Quadratic is the true analog. And as for metrical result, so the analog of the result by Einsiedler, Katak, and Lindenstrauss was proved by Einsiedler and Kleinbach perhaps in 2007, if I remember well. So they proved that the set of exceptions to the, say, p-adic Littlewood conjecture as of dimension 0. Okay. But actually, they didn't prove them. So they prove a bit more, but it's not possible. It doesn't seem to be possible to deduce from their more general results the analog of this. So, but we'll nevertheless keep this. Yeah.
What happens if the limit always exists?
The limit always exists because P of n plus n prime psi is at most Pn psi times Pn prime psi. So yes, we'll keep this this point of view of entropy or complexity of a real number, which means the complexity of its continued fraction expansion, and we'll see what can be said on this p-adic Littlewood conjecture using this point of view, so that this is a joint work with Dmitry Badziain, so Manfred Einsiedler, and Dmitry Kleinbach. So basically what we proved, and I will give more details, that that's the analog of this result on the one hand, and in the other hand, that if the complexity of alpha is too small, then the conjecture is true. So the conjecture is true if the complexity is large and if the complexity is very small. So first, if the entropy of alpha is positive, then periodic Littlewood conjecture holds. So I will give no details, but there is some extra work to be added to what Einsiedler and Kleinbach did in their paper. So it's not a straightforward corollary. Okay. And for small complexity, can write the result as follows. So if there exists positive C such that P n alpha is less than n plus C for every n, then so the conjecture holds for every P. So in particular, this is true for when alpha is Sturmian. Well, it's true when alpha is Sturmian or quasi-Sturmian. Actually, as I will explain, this is true for a more larger class of alpha that it doesn't translate to complexity. So actually, we have this combinatorial statement saying that let's say AG be a bounded sequence of positive integers.
Sorry, I didn't understand. The first term does not imply the second one. So
no, not directly. So there is some.
So if P n of alpha is at most n plus C, then the entropy is 0.
Ah, yeah, here. Yeah.
Yes.
Yes, I know. Yes. They are both unrelated.
Okay. So you first proved the second.
Yeah, I will not say more on the first one. I will concentrate on the second one. Yeah. So assume that this sequence is recurrent. So which means that every finite block occurring in the infinite word A1, A2, A3, etc. occurs infinitely many times. Okay? So every finite block which occurs one time occurs infinitely often. Then alpha whose continued fraction expansion is given by this sequence A1, A2, A3 satisfies the periodic Littlewood conjecture. And I will give the proof. So the proof is very easy if you and uses basic results from the theory of continued fractions. So I start with my sequence AG, which is, as I said, recurrent. And this implies that there exists a sequence nk, k at least 1, such that nk plus 1 is at least 2 times nk, which I don't really need this. What is important is the following, that A1, A2, A, and k is a suffix of A1, A2, A, and k plus 1. I mean, I use the fact that the prefix of length nk occurs infinitely many times in my infinite word. So then I can define, it's not unique, but I don't care, I can define such a sequence. So there is a fact that if I is less than G, then A1, A2, A, and I is a suffix of A1, A2, A, and G. A1, A2, A, and I is a suffix of A1, A2 up to A and I plus 1, which is a suffix of A1, A2, A and I plus 2, et cetera, up to A1, A2, A and G. It's okay, or you need a picture? So this is the first fact. The second fact is a fact from the theory of continued fraction. First of all, I will write say P. Okay. Pn over Qn is n's convergent to this, to my continued fraction, to alpha. And there is a following fact Qn minus 1 divided by Qn is 0, n minus 1, a1. Okay. You simply reverse order of partial quotients. So, thus, when E is less than G, we have that Qni minus 1 divided by Qni is a convergent to Qng minus 1 divided by Qng. Because they have their first partial quotients in common. So the first partial quotients of Qng minus 1 divided by Qng are exactly the partial quotients of these fractions because a1, a2, a and I is a suffix of a1, a2, a and g. So this means that Qng minus 1 divided by Qng minus Q and I minus 1 divided by Qni is less than 1 half over Q and I squared. Okay? So this will be. Just interrupt me if something is not clear because it's really not difficult. I can give more details if needed. So, now I take some integer L and that modulo L, the pair Qn minus 1 takes at most L squared different values. So by the box principle, so there exists integer ag with 1 less than I less than g less than L squared plus 1 such that so Qni is congruent to Qng model and Qni minus 1 is also congruent to Qng minus 1 model. Okay. So we find the integral Q to be Qni Qng minus 1 minus Qni minus 1 Qng. Okay. And we will evaluate Q times Q alpha. So Q times Q alpha, or say, so Q alpha is at most 2 times Qni times Qng minus 1, using the fact that Q minus 1 is less than 1 over q and g. So by basic properties of continued fractions. So we have this. Also, I want to estimate q. Q is equal to qni times qng times this. Okay, which is exactly the quantity that I have estimated here. So it's then less than qng qni minus 1. Okay, it means that q times q alpha is less than 2. And if one considers this property, one sees that L divides Q. Okay, this is, so we have Q times Q alpha, which is bounded independently of Q, and small l, which divides Q. So if you take for L, say, take for instance, L is P to the A for prime P, then you get that Q alpha QP will be less than P to the minus A. So then you can approach 0 as much as you want. Because you can take A arbitrarily large, so you have this. But actually we have, this proof gives much more. And because here L is any fixed integer. So consider the following problem. So again alpha real, and define C of alpha to be the limit of Q alpha. I will assume that alpha is badly approximable, otherwise it's not interesting. It's something that, like the Lagrange constant, depends how you define the Lagrange. Usually you like to define the Lagrange constant. So it's not difficult to see that if you multiply alpha by n, then the Lagrange constant of that, then the C of n alpha is at most n times C of alpha, and at least C of alpha divided by n. So it could be interesting to consider what can be said on the sequence C of n alpha of the sequence C of n alpha when n goes to infinity. So there is a interesting result of Einsiedler, Fishman, and Shapira, saying that the infimum of C of n alpha is 0. for every alpha. And there's a problem, which I know that since this morning that it was proposed by Michael Boschanitsa. So I didn't know that before. So oh. No. Ah. So is it true that Cn of alpha tends to 0 when n tends to infinity? And this question remains completely open. But at least it's true for when the continued fraction of expansion of alpha is recurrent. It follows from what I have written here. Let me give more details. So if A1, A2 there is recurrent, then alpha satisfies C of n alpha is less than 2n for every n. So we cannot expect much better because Cn of alpha is greater than some constant over n. So it decays as fast as it could decay. And the proof follows from what I wrote here. So take L fixed. And so there are arbitrarily large integers Q such that L divides Q and Q alpha is at most 2. Q is LQ prime. So you have Q prime L alpha, which is less than 2, or if you prefer, Q prime times Q prime L alpha is less than 2 over L. So this means that C of L alpha is less than 2 over L. So very recently, don't know exactly I don't remember the names of, so Fishman, Simmons, maybe Broderick, proves that the set of badly approximable number alpha for which Cn of alpha decays like this with constant instead of 2 as full Hausdorff dimension. So it's quite a large set. But so this question, which I believe is very interesting, remains open, and a positive answer to this question would imply a positive answer to the periodic Littlewood conjecture, which is almost clear. And well, yes, it's probably at least Batzian things, and I'm inclined to think also that the answer should be negative. But well, I prefer to say that it's a problem rather than a conjecture in this sense. Okay. Thank you.